Hey guys, it's Miss Johnson and I'm here to bring you our notes for Unit 7 Notes 3, which is on calculating the z-score. So we've spent a couple of days talking about normal distribution and that normal curve that's in your z-score table that you have. And today we're going to talk about how we actually find those z-scores and what our formula is. So remember that a z-score is the number of standard deviations a given score is above or below the mean. So it's on that normal distribution curve where your mean is 0 and your standard deviation is each 1. Now, the problem is in the real world, our data doesn't always have a mean of 0 and a standard deviation of 1. So what we do is we normalize everything by fitting it into the z-score table by giving it this z-score. So we would take whatever our mean is, would take whatever our data is, subtract the mean, and then divide it by the standard deviation to get that z-score. So today we're just going to do some practice with that formula of finding our own z-scores for the normal distribution. So in example 1, it says, find the z-scores given of a mean of 12 and a standard deviation of 4. So if I want a mean of 12, or if I have a mean of 12 and my data is x equals 14, that means that my z-score is going to be the data minus the mean of 12 divided by the standard deviation of 2. That's the same thing as standard deviation of 4. That's the same thing as 2 divided by 4, and 2 divided by 4 is 0.5. So our z-score is positive 0.5. So calculating that z-score, you take the data minus the mean divided by the standard deviation. So taking a look at part B, I would have a z-score of, and you can kind of start to envision what's going to happen here. 14 is pretty close to 12, which is the mean. 22 is a lot farther away from the mean of 12, so your z-score should be quite a bit higher here. Here it would be 22 minus 12 divided by 4, which is the same thing as 10 divided by 4. And now I have a z-score of 2.5. So much farther away, which means it's many more standard deviations away from the one that was a lot closer to 12, to the mean. And then of course you have data that is less than the mean. You still always have to take the data minus the mean. So I'd have a z-score here of 7 minus 12 divided by 4. That's the same thing as negative 5 divided by 4, which is the same thing as negative 1.25. So that's on that negative side of the z-score table, which is the bottom 50% of the data. Remember that your mean marks the 50%. So positive z-scores give you the top 50% of the data, and negative z-scores give you the bottom 50% of the data. Anything that's below the mean is under 50%. Is in the bottom 50%. Anything that's above the mean is in the top 50%. So we're just normalizing our data today. So find x. Now we have a different variable to find. Find x given a z-score of negative 1.1, a mean of 400, and a standard deviation of 10. So recall that the z-score formula looks like this. It's x minus the mean divided by the standard deviation. So in this case, I know the z. Z is negative 1.1. So I'm going to plug that in over there for z, and I don't know x. That's my question. So x has to stay a variable. I subtract the mean of 400, and I divide it by the standard deviation of 10. Now we have to go back to our good old algebra skills here and undo this equation. So if I'm going to undo this equation so that I can, because my goal is to get x by itself, that's what I'm trying to find. Undoing this equation, I would multiply by 10 to get that 10 out of the denominator. 10 times negative 1.1 is negative 11. Over here my 10s are gone and I have x minus 400. Then I still need to get that x alone, which means I need to add 400 to both sides. And negative 11 plus 400 is 389. So my x value there is 389. So this one I was missing the x. So I had to use my algebra skills to undo all of that stuff to solve that equation for x and get my x variable. Let's take a look at example 3. It says the ACT has a national average of 21 with a standard deviation of 6. The z-scores of students are given below. Find their actual scores. Z-scores of students are given below. Find their actual scores. So this is another case where I have the Z, their actual scores is the X. So the X is the missing part. So we have three people here. We have Scott, Lindsay, and Mike. We're going to work on Scott first. So for Scott, I have a Z-score of negative 1.32. That's going to go on the left side of my equation by itself because that's my Z. Then I don't know the data and I need to subtract the mean, which is 21, and divide by the standard deviation, which is 6. So solving that, I multiply by 6 to cancel the denominator, multiply by 6. That gives me negative 7.92 equals x minus 21. And then I add 21 to both sides, and I get 13.08 is equal to x. Now here's the thing, we also have to consider our data. So I'm looking at ACT scores. Now, to my knowledge, I have never seen an ACT score that is a partial score. They always give ACT scores as a whole number. So if you're looking at this as your x based on all of this data up here, that means that his score was probably 13. So that's what Scott got on the ACT. Kind of a sad panda. Not the best score for Scott. That's okay. Let's try Lindsay. So now here's the thing. Scott's Z-score was negative 1.32. So you knew it was going to be in the bottom half of the data. So you knew it was going to be underneath the mean of 21. Now Lindsay, she has a Z-score of 2.15. So her Z-score of 2.15 is going to be well above the mean. So let's see what Lindsay got here. So 2.15 is equal to whatever Lindsay's score is minus the mean of 21 and divided by the standard deviation of 6. So again, you got to get rid of that denominator. That cancels the 6 over here. 6 times 2.15 is 12.9. So 12.9 minus is equal to x minus 21. And then I need to take the 21 and add it so that it goes over to the other side. That cancels that. 12.9 plus 21 is 33.9. Which is equal to x. So again, I'm looking at whole number scores here because this is ACT, so that probably means that Lindsay's score was a 34. Go Lindsay. That's a really nice score for the ACT. So now let's take a look at Mike. So his score is 0.46, which is still a positive Z-score, although it's much closer to the mean. It's much closer to that 0 mark, which is marking the mean. Z-score is pretty low. So you're still going to be up above the 21, but maybe not too many points above the 21. So Z-score of 0.46 is equal to x minus the 21 over the 6, which is your standard deviation. Multiply both sides by 6. That cancels that. 6 times 0.46 is 2.76. And then I need to cancel that 21, so I'm going to add 21 to both sides, which makes that go away, and I get 23.76 here is equal to x, which again, I'm going to round that to the nearest whole, and means that his ACT score, Mike's ACT score was probably about a 24. So calculating Z-scores. Sometimes you got to work backwards. All right. Let's take a look at example 4. It says scores on the Wechsler Adult Intelligence Scale, or in other words, the standard IQ test, are approximately normally distributed within age groups. So for the 20 to 34 age group, the mean is 110 and the standard deviation is 25. For the 60 to 64 age group, the mean is 90 and the standard deviation is 25. So Sarah is 29 and her mother Ann is 62. Sarah scores 135 on the Wechsler test while Ann scores a 120. Who has the better score relative to her age group? So here's the question here. This is the exact reason that we have Z-scores and the normal distribution curve in the first place. These are two different women of two different ages that are classified into two different groups. So it's not fair to compare them as they are right now because they're in two different age groups and those age groups have different means. Their standard deviation is the same, but their mean is different. So we have to normalize them. We have to put them on the normal curve, which allows us to compare them to each other based on their Z-score, telling us how far are they from each's individual mean. So I'm going to find the Z-score for both people. I'm going to start with Sarah because it says Sarah scores 135. So for Sarah, She is 29, which means I'm in this world right here. So Sarah's z-score is 135 minus the 110, which is her mean for her age group, divided by the 25, which is the standard deviation. When I calculate that out, that gives me a 25 over 25, which means she has a z-score of 1. So Sarah's z-score, Sarah's normalized score to the normal curve is 1 standard deviation away from the mean and above the mean because it's a positive 1. So now let's take a look at Anne. For Anne, her mom, Anne is here in this age group. Anne is 62. So her age group has a mean of 90 and a standard deviation of 25, and Anne scores 120. So her z-score is 120 minus the 90 divided by 25, and check it out. She has 30 points divided by the 25, which means her z-score is 1.2. So she's 1.2 points for standard deviations above the mean. The person with the higher standard deviation is, or the higher z-score, I should say, the person with the higher z-score is the one who has the better score relative to her group. So even though Anne has technically a lower IQ compared to Sarah, whose IQ was 15 points higher, Anne's normalized standard deviation or normalized z-score is higher than Sarah's. So Anne has a better score respectively. Respective to her age group. All right. So that is how we calculate z-scores. That's our z-score formula. You're going to use that formula anytime you need to normalize something, put something on the normal curve, and you're not given the z-score. You always want to take data minus mean divided by standard deviation, and that will allow you to put it on that normal curve. That's all I have for our notes for today. Thanks for watching, and I will talk to you next time.